This will be a video on section 9.4, Divergence and Integral Test. So we're going to start with Divergence Test, and it's also called the nth term test. You need to know both of those names. I know in AP tests I've seen them called nth term test, and if you don't know what that means, you might be a little confused. So the divergence test is something that is often used first, and oftentimes it's easy to see whether it passes this test or not. And what the divergence test does, it only quickly identifies divergent series. It does not identify convergent series. It's an important thing to realize. So it does not prove convergence. It just quickly proves divergence, and therefore saves us some time if we recognize that. And what does this say? What are the conditions? So first of all, you need the terms of your series to approach zero. Okay? So this is what it's saying. If a series, infinite series, is going to converge, the terms must get smaller and smaller and approach zero. Now, what it doesn't say if the terms approach zero, then it converges. It does not say it backwards. Do not confuse yourself with that. That is not true, and we'll see some examples of that. Now, here's the equivalent statement. If the terms do not approach zero, then the series diverges. That's the one that you will use this for. If the terms do not approach zero, the series will diverge. And that should make sense to you, because in infinite series, you're adding a bunch of things up. And think about this. If these terms aren't zero and you keep adding them forever, it's just going to get bigger and bigger and bigger. It's without bound. The only possible way that these would approach a number is if the terms get smaller and smaller and smaller and do approach zero. So think of it that way. And just because it's getting smaller and smaller doesn't mean it'll converge. Just because you have a barrel and you're putting smaller and smaller drops of water in it doesn't mean it's not going to overflow. It depends on how quickly and how small those get. But you're guaranteed, if the drops of water are not getting smaller and smaller, that barrel is going to overflow if they're not approaching zero. So that's what the divergence test or the nth term test does for you. It quickly identifies divergent series but does not identify convergent series. So here's how you would do this test. Now, hopefully you guys are pretty fast at recognizing limits. You look at that and you should, by experience, hopefully from last year, know that that limit's not zero. Let's go through the process. There are two ways you can do this problem. This is an indeterminate case because you get infinity over infinity, and that's indeterminate. And you learned you could divide everything on top and bottom by k. In actuality, I'm multiplying by 1 because this equals 1. And you learned you're allowed to multiply anything by 1 and it doesn't change it. So you get 1 over 1 plus 1 over k. And if you remember, one pizza divided by an infinite number of people, you're not getting any pizza. So this limit is 1. And since that limit is not approaching 0, it doesn't have any chance to converge. We still don't know if it converges, but we know this series diverges for sure because the terms do not approach 0. Now the other way you could have done this limit, you remember L'Hopital's? If you have an indeterminate case of 0 over 0 or infinity over infinity, you can take the derivative of top and bottom separately, and that limit will be the same as your original. The derivative top is 1, The derivative of the bottom is 1, and it's 1. And since the terms do not, the terms do not approach 0, this is a divergent series. El Duno with that one. This one's a little trickier. So we take the limit as k goes to infinity of 1 plus 3 to the k over 2 to the k. And you will see as k goes to infinity, you have infinity over infinity, which is indeterminate. So you have a tougher situation here. One thing you could try, you could try dividing by 2 to the k. We can see what happens with that. Honestly, I'm not even sure where that will get us at this point. Then we would get this 1 over 2 to the k plus 3 to the k over 2 to the k over 1. And let's see what happens here. This will get us the limit as k goes to infinity of 1 over 2 to the k plus 3 over 2 to the k. Now, we are in a good position right now because let's look at this. That goes to 0. But this is a number bigger than 1 going to infinity. That is going to be infinity. Since that does not approach 0, this will diverge also. So that's what's going on with that example. We have 2 more examples to go through. We'll keep on going. Let's do the next one. So this next one is going to become a very familiar series for you. It's called a harmonic series. It will become a friend to you because you're going to see it a lot. But the limit as k goes to infinity of 1 over k is 0. So do we say this converges? No. Divergence test only proves divergence. So in this case, it might or might not. We still don't know what's going to happen. And then part D. Again, we look at this. And 1 over infinity is going to be 0. Again, we don't know what's going to happen to this. It has a chance to converge. We haven't eliminated it yet, but we still don't know. That's the divergence test. Okay, so the harmonic series is this. 1, 1/2, 1/3, 1/4, 1/5, forever, ... Now, this series diverges. Even though the terms get smaller and smaller and approach 0, it diverges. That's just a theorem. So from now on, whenever you see a harmonic series, by this theorem, you know it diverges. And I'm going to show you why. And this, some of you may follow this okay, and some of you may be a little confused. I'm going to break these into different groups. Here's my first group. My second group is here. My third group, I'm going to pick off 2 of these, and then I'm going to take 4 of these, and then I'm going to take 8 of these. So I'm going to start with 2 terms, 4, 8. The next set's going to be 16, then 32. Why am I doing this? You will see. That's 1, and that's 1/2. Here is what I can claim. All right, don't you agree that, okay, I'm going to write this. 1/4, let me get rid of these numbers here. 1/4 is going to be smaller than 1/3. Do you agree with that? So if I replace this 1/3 with 1/4, the sum is going to be smaller. So I'm going to put a 1/4 there and a 1/4 there to replace that. Now, if this is smaller than that, then I can say that this sum of this series is going to be smaller. Let me change this now. Or in other words, this series is going to be bigger than that because I replaced this with something smaller. Now I claim that 1/5 and 1/6 and 1/7 are all smaller than 1/8. So if I replace all of these with 1/8, this is smaller than this. So making all of this even more smaller, if that is even the proper English than that. And then I claim all these numbers, 1/9, 1/10, 1/11, all the way to 1/15. All of those are smaller than 1/16. I actually think I went the wrong direction. Let me see if I'm doing that right. Those are bigger, huh? Because the denominators. Okay, let me back up. These are bigger. I need to switch these inequalities. I'm not even thinking right. It's getting late. So these are bigger. No, 1/3 is bigger than 1/4. 1/4 is smaller than 1/3. Oh, I'm comparing it to the... Okay, I know what I'm doing. Whew. Yoshida. Okay, we are correct. 1/4 is smaller than 1/3. So since 1/4 is smaller than 1/3, if I put a smaller thing here, this will be smaller. Now, I did the wrong things here. 1/8 is smaller than all of these. So if I replace all these with 1/8, this is even smaller, so we're good with that. And then this is the wrong direction. 1/16 is smaller than all of these. So if I replace all these terms with 1/16, it's going to take a while here. I wish I was faster. Since 1/16 is smaller than all of these are smaller than all of these, therefore we're doubly sure about that. And so look what's happening with our series. We have 1, we have 1/2. If you add all these up, that equals 1/2. If you add all these up, that's 4/8. That equals 1/2. If you add all these up, that's 8/16. That's 1/2. And I claim if we keep on doing this forever, we add 1/2 forever. ... That means this right side is divergent. But this is bigger than the right side, so that's divergent. So that's kind of the process of showing why the harmonic series diverges. If you like that, awesome. If not, oh well. Integral test. So, the function must be continuous, positive, and decreasing to apply the integral test. So that's what we're doing here. And here's what it says. Suppose I have this series, and I want to know if it converges or diverges. Now, if I notice I'm able to integrate this term, if a sub k is integrable, then I can integrate this thing, and whatever this does, if that converges, that converges. If this diverges, this diverges. They both do the same thing. So either both converge or both diverge. Okay, so that's what it's saying. In the case of convergence, the value, this is huge. I'm going to underline this. the value of the integral is not equal to the value of the series. So just because you find this equal to some number c doesn't mean the series adds up to c. Very important. In fact, you can kind of figure out if this is bigger than that or smaller than that. There's ways to do that. But don't assume that this integral is equal to the sum of that series. So what you want to look at is example A. And you will notice, since k starts at 1, that this will always be positive. Now, it's always decreasing because the bottom grows faster than the top. Now, you could take the derivative and find the derivative is negative to prove to yourself that it's decreasing, but we're good with that. And it's continuous because k is a continuous polynomial, that is a continuous polynomial, and a continuous function divided by a continuous function is continuous as long as the bottom's not 0, and that bottom is never 0. The next thing I would have to do is recognize, hey, I can integrate this. I know how to integrate this. So I go 1 to a, the limit as a goes to infinity, it's an improper fraction. I'll use x's. I like x's. And this turns out to be a u sub. If I make u the denominator, du is 2x dx. And here's the question. Do I have 2x dx here? Not yet, but now I do. So I can rewrite this. This whole top becomes du, and the bottom, we defined it as u. So we have du over u. Now we need to change, that's an x. If I plug 1 there, u comes out to be 2. And if I plug a into here, u comes out to be a squared plus 1. Now the antiderivative of that will be ln absolute u from 2 to a squared plus 1. I forgot my limit in front, which equals, now I plug in a squared plus 1 minus ln 2. Now at this point, ln of infinity is infinity. This is a constant, so we can say this equals infinity. Therefore, this series diverges, or this integral diverges. But the integral test says, since this integral diverges, therefore this series diverges. So that's part A. Let's continue going. That's the first example. Let me erase this stuff. I'm actually going to make sure my answer's right. It looks like I got the same answer as they did, so I'm happy. Let me erase all this. And we're going to do letter B. And letter B again, you might notice, hey, I can integrate this. So you write this as 1 over square root. I'm going to do x's again. I just feel more comfortable with x's. You can do k's, dk's, and all that, but variables don't matter. It's a u sub again. U is the 2x minus 5. Du would be 2 dx. And I say to myself, self, do I have a 2 dx? No, I don't, but now I do. So let's continue on here. So the top becomes du, and the bottom is radical u. And when I plug a 3 in for x, that's 6 minus 5, that's 1. And I plug in an a in for x, that's 2a minus 5. Now this remembers u to the negative 1/2 power. So when I integrate that, this is what's going to happen. Uh-oh, I don't need that. I'm going to integrate that. So it's u negative 1/2. I add 1 to the exponent and divide by that 1/2. and I'm going from 1 to 2a minus 5. So what do we have here? We're going to plug in the 2a minus 5, and then we're going to plug in the 1. And so again, when we plug infinity here, square root of infinity is infinity minus a constant. It's not going to affect it. We're going to get an infinity, and so we again are going to get divergent. So we will say this diverges, therefore our original series diverges. And we have one more example to do. We are going to do C. We have to integrate this. This one, wow, this is going to test your memory. Some of you need to review some of your derivatives integrals. I'll do x squared plus 4 dx. All right, once upon a time, you knew something. You knew the integral of 1 over x squared plus 1 dx was arctan x plus c. And then you say to yourself, self, I wish that 4 weren't there. So as some side work, I am going to do this. I'm going to rewrite this by taking a 4 out. That gives me x squared over 4 plus 1. If you don't believe me, distribute that and you do get that. Then I can rewrite this as 4x over 2 squared plus 1. And so I'm going to replace and rewrite this original with all that. So integral 0 to a, 4x over 2 squared plus 1 dx. Now this 4 is a constant. I'm just going to pull it out in front. And then we have that. Now we're so close to that, but we have x over 2. That's a u sub. U is x over 2. du is 1/2 dx. And here's our question. Do we have a 1/2 dx here? We don't. But now we do. Now I can rewrite this. So this will be the limit as a goes to infinity. And this is a good review for last year in integrating u squared plus 1. Now, this is 0, believe it or not. You put a 0 there, it's still 0. And this is a. We're going to get a over 2. Now, we get arctan of u from 0 to a over 2. Let's do this. Arctan of a over 2 minus 1/2 arctan 0. Let's do the second half. What angle has a tangent of 0? 0. That's just 0. That's easy. Okay, here's where it gets fun. Put infinity. What angle has a tangent of infinity? Golly gee willikers, do you know what your tangent function looks like? Do you know it looks like that? And this is pi over 2 and negative pi over 2. Why is that? Review, tan x is sine x over cos x. And hopefully you remember from last year, a vertical asymptote happens when the denominator approaches 0 and the top doesn't. The cosine of what angle is 0? Pi over 2. So this answer is pi over 2. So this integral is pi over 4. This integral converges Therefore, that means the integral must also converge. Now, a side note and a reminder. This series, let me get the original, 1 over k squared plus 4, does not equal pi over 4. Just because the integral approaches pi over 4 doesn't mean the series approaches pi over 4. Don't make that mistake. I could probably give you a good argument for this. Should I? I'm not going to do it right now. We'll approach it at some point. Maybe at the end of this video. We'll see how we feel. Alright, a new series you have to know called the P series. It's 1 over k to the p. Now what does that look like? If you write it out, it's 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p plus dot dot dot. Now that might look familiar to you because if p is 1, that's your harmonic series. So what does this say? In order for this series to converge, p must be bigger than 1. If p equals 1, diverges. That's your harmonic. If p is less than 1, diverges. So that's what you have to know. So these problems are actually pretty easy. Let me rewrite this series. It's 1 over k to the 3/4. This converges because diverges. Whoa. Diverges because p is less than 1. Okay, this one's crazy. I apologize in advance. This one takes some thunking, but it's good thunking. Alright. I might say to myself, man, if this were only k squared, I could say for sure this is a convergent P series because p is greater than 1. How can I do that? Let's look at what these terms are. Let's plug in some numbers. If I plug in 4, I get 1 over 3 squared. I plug in 5, I get 1 over 4 squared. 1 over 5 squared, dot dot dot. So I can actually rewrite this like that, but I just have to start with the right number. I want to get 1 over 3 squared, 1 over 4 squared, 1 over 5 squared. So think about this. What can k start at here to make that happen? Well, I want to start with a 3, so k starts at 3 to infinity. These are equivalent statements. If you didn't follow that, you should kind of rewind the video and process through that and make sure you get that. These are equivalent. Therefore, this series converges. Why? Because it's a P series with P greater than 1. El Duno. So that's your lesson on P series. So there's a lot of nuances with series, like this one I just did where we re-indexed and rewrote it. And there's a lot of subtle things. You need a lot of practice. So let's talk about these properties. So you have a series and you know the terms add up to A. But now you have C times the series. Well, quite simply, this is equivalent. You can factor the C out. The series sums up to A still. So now the new series will add up to CA. You just multiply the old sum by the new constant. So you can pull a constant out of a series. That's what it's saying. The next one. So A sub k converges to A. So you have a convergent series. And B sub k converges to B. So you have two convergent series. So if you have a new series where you add up the terms, okay, here's the good news. You can just take the sum of the first series and combine it with the sum of the second series. So that's a pretty simple one. Okay, this is the one that I'm going to try to work with your brain and see if you can follow this. Number 3, what is it saying? So I'm going to start at 1 and go to infinity for this series. So I get a sub 1, a sub 2, a sub 3, dot, dot, dot. Now, they're going to say this to you. Instead of starting at 1, I'm going to start at a different number. So I'm going to start at a sub m plus 1, a sub m plus 2 plus dot, dot, dot. Here's what this theorem says. It doesn't matter if you start at 1 or 2 or 100 or 1,000,000. It doesn't matter your starting point. Both of these series will do the same thing. If the first one converges, then the second one converges. If the first one diverges, the second one diverges. And here is the reasoning. I'm going to draw the partial sums, not the actual terms of the series. These will be partial sums. So S sub n, and these are the number of terms. And if a series converges, the partial sums will approach what it converges. We'll say it converges to L. So suppose this is series A sub k. That's the series. So take this series, and what if I add 1,000 to that series? Now think about what happens. I'm going to lower this. I should have given myself some room. If I add 1,000, so A sub k converges. Now I add 1,000. What's that going to look like? That is a vertical shift up 1,000. Your new series is going to do this. And now it's going to converge to a new number, L plus 1,000. It's not going to change whether it converges or diverges. We just added 1,000 to each point, and it moves up. So, all it's saying, I can add or subtract any constant in front. All it does is shifts up or down, but if it converges, it's still going to converge. And if the original diverged, the new will diverge. So, it doesn't matter where you start in a series. So I have two of the same series. One starts at 1, one starts at m. So this one is going to be bigger because you have all these extra terms in front. Now at some point, you're going to get to that m. So what's the difference between these two? Well, this first one has all these extra terms in front. So it's just going to be bigger. It's just going to be shifted up. So you got to understand, this is important. Adding or subtracting terms to a series does not change its divergence or convergence. And that's it for this lesson. Bye-bye.